I'm recording.
Sorry. Okay, so our next speaker is Shengxuan Liu from Warwick, who's going to be speaking about stronger Bogomolov Gieseker inequality of Bridgeland.
Yeah, thank you very much for giving the opportunity. Today I will talk about stronger Bogomolov inequality and the Bridgeland stability conditions. Yeah, please. And during the whole talk, my variety will always be. Oh, sorry. Something wrong?
No, you have to click here on the mask, because otherwise we can't hear you.
Oh, maybe I remove it. Oh,
No.
oh, under the
mask.
mask.
And click the microphone on the mask.
Ah, I got the point. Sorry. Like this. Oh, inside the mask maybe. Oh, middle. Yeah. Okay. Better. Yeah, sure. Thank you. Okay. Yeah. Yeah, and all the variety I will use today will be smooth projective over C, or complex numbers. Yes. And to talk to you about what is the Bridgeland stability, maybe I go to the traditional word, which is called the slope stability. So let X be a variety of dimension n and h be an ample line bundle. Then we define for the slope is that we take f to be a sheaf on X. Then the slope of this sheaf with respect to this ample line bundle is given by hn minus 1, 1 times f over 10 h times h to the power n 10 0 of f if 10 0 of f is not equal to 0. And we will take it to be plus infinity if 10 0 of f is equal to 0. And another one you will read from Harshon is that it's in the curve case, this will be given by degree of f, cosine rank of f, if rank f is not equal to 0, and will be plus infinity if rank f is equal to 0. And we say that f is semi-stable or stable if for all the non-trivial subsheets E inside F, such that the slope of E is smaller or smaller or equal than the slope of F quotient E. Yeah, it may be a bit different from the definition you see, because the traditional definition will only consider about the vector bound. This is for some technical reason we take this one, but they are more or less the same by seesaw lemma. Yeah, and if we give this definition, so we have the following property, which is given by the following theorem. For every shift f on X, there is one unique filtration which is called the Harder-Narisman filtration, given by the following things. You take 0 to be the first term and taking the strict inclusion up to a finite term, you go back to f, such that the quotient of them are semi-stable, and the slope of them are strictly decreasing. So this is a very good property, saying that if you want to study a sheaf, you can always consider a filtration that only consider a study about semi-stable things. Actually, there's another one to reduce to a stable one, but I will not talk about them today. And so let's define the following function, saying that if you take the sheaf f, you define it to be this way, to be minus hn minus 1, 1 of f plus I times h of n 10 0 of f. I suppose if you consider a curve, then we use the minus degree of f plus I rank of f. Then if you take any shape, then it actually tells you that you will take them to the prospective slope, where the slope is actually given by the slope of them, this slope of them. So you map to this picture. And the point here is that if you consider a kernel of this map, you have the following two different cases. Suppose it is a curve, then actually it only have the trivial kernel. But suppose it is higher dimensional case, then actually it's not trivial. One of the examples you can consider, like skyscraper shape, is always inside the kernel. So this saying that if you consider the slope stability, you are losing some information in the higher dimensional case, which you don't want it to happen. So this is why people are consider something called Bridgeland stability. The key idea of the Bridgeland stability is that we change the category we think. The categories we think here are coherent shape of X, but here we will consider something called a heart. So a heart is a full additive subcategory of dBx, where dBx means the bounded derived coherent shape of X. Yes, bounded derived category, such that it has the following property. Oh, I should use, let's say that I use A to mean a heart. The first one is that there's no home from the large shift to a smaller shift. And the second is that if you take any object inside the derived category, we have something like a filtration. Means that we have a train of maps in the derived category. And you consider the mapping cone of them. Then AI are inside the heart, shift some number Ki, and the shift are strictly decreasing. Oh, sorry. So example of them are, so maybe I can draw a picture to show what I mean. What is the definition giving you is that if you consider this whole rectangular to be the bounded derived category, the hard thing that you can divide them into some smaller categories, which are more or less similar to each other. Yes, this is what the heart is doing. So example of heart. The first one is the coherent shape of X. And the first, and the property one is because that in the derived category work, if you take an object shift I, an object shift J, this actually is equal to the extension group of I minus J, or J minus I, of A prime. So it will be 0 if you take I is larger than J, right? Because by definition. And the second one is that for every twin complex, you can always take the cohomological filtration. So it has the property too. Another heart that we will always use in the, it's very popular in the stability condition, is the tilting heart. And I will only read one example of them. Suppose we define that coherent beta, Suppose we consider the following two subcategories, T beta H, defined to be all the objects inside the coherent shape of X, such that if you consider the HN filtration of it, the smaller one of the slope is larger than beta. And if you, and similarly, you consider the F beta H, it's all the object, so that if you consider the HN filtration, then the largest one is more than or equal to beta. Then you consider the coherent shape beta H of X, defined to be the extension of F shift 1. And the T beta H. This will giving back to a heart, which is called a tilting heart somehow. So what is the second example doing is that if you consider back to this picture, we are subdividing each block into two smaller blocks, where it's given by T, F, T shift 1, F shift 1, something like that. But you don't dividing them by this way, but shift a little bit. You consider this new block, which giving you a heart. And yeah, actually the proof just read more or less just translation of this picture. So given a heart, we are, and to giving a definition of stability condition, we will use a finer structure than this one. Which is called a slicing. The slicing is a family of them, of a fully additive subcategories, where phi is graded, where they are graded by R. So that it has the following properties. First is that if you consider one more of them, it is the original one, shift one. The second one is that you still don't have the home from the larger one to the smaller one. And the third one is that you have also the filtration property, like the one given before. And the second one is actually, if you think about the traditional stability, it's saying that you don't have the homomorphism from a larger slope to a smaller slope of them. So back to the picture, what is the slicing doing is that you subdividing the block, but not graded by J. You are subdividing the block by graded by R, so you can even finer dividing of them. Or it's given by P phi, P per psi, something like that. So the definition, so I can now give in the definition of the Bridgeland stability. So a Bridgeland stability is a pair given by P, Z, where P is a slicing. And Z is a function from the numerical K group of X to C, which is a group homomorphism actually. And this is usually called central charge. And you only have one following restriction: the image of P phi. Oh, maybe writing this way. If you take a non-zero object inside P phi, then the image of it is inside R larger than 0, E I pi times phi. So it's like the similar picture we are doing here, that if for every object you take into the respective slope. But because of this property, you require that there's nothing that has a trivial, that is inside the kernel if it's not a trivial object. And back into this picture, you see that slicing are divided by graded by Z. But if you consider the whole block here, then if you consider something of all the collection of from 0 to 1, then actually you are getting back to a heart. So this is actually giving you following the proposition. So the proposition is that the Bridgeland stability I should mention that actually there's one more requirement called something called support property, which is only a technical requirement and I won't write it out. And so the Bridgeland stability is equivalent to a pair where A is a heart, and Z is something, Z is a function from A to C, such that you have the following property. The image of Z, of F, is inside upper half plane. And suppose imaginary part of an object is equal to 0. This implies that the real part of this object must be smaller than 0. So it excludes the possibility that having a trivial kernel, so having a non-trivial kernel. And then you define the slope of this object to be the minus of the real part of this function, cosine the imaginary part of this function. And you can define the stability with respect to this this notation by the similar notation that you consider some object, it must have a smaller or smaller equal to slope. And the second that is saying that you have some H infiltration property. Means that if you take a non-trivial object, E, inside the heart, it has a filtration inside E1, inside E2, up to En, which is equal to E, such that EI, cosine EI minus 1, are semi-stable. And the slope of them are strictly decreasing. And this is just exactly what the H infiltration of the classical world, but it also has this property. And the third one is the support property. And exactly the same properties, same writing out, but it's very technical, so I omit it here. So now a natural question is that when the stability exists, when the Bridgeland stability exists. And today I will talk about one possible solution to prove that the existence of Bridgeland stability. The first one, so this is part 3, that when the stability of a manifold exists. The first case is the curve case. Then actually it's the traditional stability condition is a stability condition. So take coherent shift of x with a function given by minus degree plus I rank of it, then you get a stability condition. Then if you consider surface case, this is a bit more complicated. Actually, at least I know that by Hubert, for all the dimensional cases, you cannot give in coherent shift x to give a stability condition. So for surface case, what you use that is the coherent shift of beta hx plus the function plus a very proper stability function will looking like this way, but you use some tilting with twisted 10 characters, then you can get a stability condition. The key point of the proof is that you need to use the Bogomolov inequality. Because you see that in the traditional world, why the thing is not a stability, because you forgot what is Chen2 doing. So you need to remember Chen2, which you can use the Bogomolov inequality. Saying that the Chen1 of it square minus 2 times H2 Chen0, Chen2 of E is larger or equal than 0 for a semi-stable object. For the higher dimensional case, like threefold, then you need to use something called the stronger Bogomolov inequality, which is very complicated. But what I can tell you that you put the Chen3 term inside it. And what you will get is that if you can prove that this one is larger or equal than 0, then this will imply that the stability condition exists. And another application of this inequality is that by Sohela and Richard Thomas, that when Q alpha beta larger or equal than 0, and it is a Calabi-Yau threefold, then higher rank DT, higher rank Donaldson-Thomas invariant are come from rank 1 Donaldson-Thomas invariant. Yeah, I think more or less it's the time now, so I will stop now. And if you have any questions.
Since we're running behind, I'm going to suggest that questions are kept for lunch and we move on to our next
Yes, sir.
speaker.
Sure.